Contrary to popular belief, your computer sadly does not have a wizard inside of it running executions. So let's take a look at how a computer physically reads code. I understand to most of my viewers this topic is rather basic, if not somewhat redundant, but since most people are taught how to print hello world on their machines yet not actually understanding how those funny pixels are being displayed on said screen is quite sad. So for those of you that like to get rid of this sadness, I must say trying to understand this process is unlike cramming before your calculus test. So to entertain the people with rather fragmentary attention spans, in short, a computer physically reads code by converting kinematic user input into binary signals, decoding them, followed by translating high-level code such as Python into low-level machine code by parse mapping, then sending the assembly code to the processor, followed by executing the instructions via the CPU, and utilizing electric circuit elements in the various computer boards to process the information at the hardware level. And congratulations, you are now one step closer to ridding yourself of that sadness. Now, going back to step 1. Users typically interact with computers through input devices such as a mouse, the Wii balance board, or whatever this thing is. These devices convert physical actions into electrical signals that the computer can understand by either touching a conductive pad or closing an electric circuit to complete a signal. And by a process known as encoding, each key press is translated into a binary sequence representing the specific scan code for that key. This encoding may involve using specific bits to represent key states such as pressed, released, or bouncing. As most of you already know, all code and data in a computer are ultimately represented in binary form, consisting of zeros and ones. Each binary digit, or a bit, are the building blocks of all digital information. But first, let's quickly look at binary out of the context of computer science. Binary was first popularized as a counting system by Gottfried Wilhelm Leibniz in the 17th century, but its absolute origins are rather scattered. This base 2 numeral system uses only 2 digits, 0 and 1, compared to the everyday counting system of 0 all the way up to 9, known as base 10. Operations in binary follow an extremely abstract format, as the 1s and 0s represent various numbers that are not 1s and 0s, yet to you, a human, 1s and 0s are numbers themselves, so thus you're forced to play mental whack-a-mole with your brain by decoding the binary numbers on the spot. However, you can also use your hands to count in binary, which looks something like this. As you can see, doing basic operations and even counting in base 2 is quite uncanny, so you can imagine my reaction when a good friend of mine recommended me the base 6 counting system. Anyways, binary here is just a way of storing information, such as in bytes, which is really just 8 bits of binary, or in the physical realm, 8 transistors, each of which can store a number from 0 to 255. And in order for these binary values to represent things like a letter or a non-base 2 number, they're converted using ASCII mapping, of which can store up to 255 values. More than enough to hold the English alphabet and most character systems, but not enough to load a PowerPoint presentation, and definitely not enough to play 3D chess. However, later on designers were able to get computers to read multiple bytes, meaning multiple sets of 8 bits, as a singular value. This is where we get things like a 32-bit system or a 64-bit system, of which the more bits it has, the more information it can process. The concept of binary counting is fundamental to computer science, as computers use electric circuits that can represent 2 states, on and off. These states align naturally with the binary digit 1 and 0. By utilizing binary as a counting system, computers can store and process information efficiently. Moving on, developers typically write code in a high-level programming language such as Java or C. These languages generally use human-readable syntax and structures, unless the programmer decides not to. However, computer cannot directly understand these languages even with batch files. Therefore, developers use softwares called compilers or interpreters to translate the high-level code into a low-level language that the computer can comprehend in a process known as parse mapping. This mapping is achieved through a set of rules and algorithms implemented in the compiler, mapping each text keyword to a specific function, and this will vary depending on the language. The compiler collects the said keywords by scanning the high-level code, identifying patterns, or the syntax in that given language, and applies predefined transformations to generate a corresponding low-level code. For example, in this line of Java code, each of the terms is organized into something called a parse tree that helps compilers trace the program's syntax of functional keywords to match binary operations accordingly. And for those of you who are rather new to computer science, think of syntax as the grammar of coding. In the following step, compilers translate the high-level code into a low-level language known as assembly, which uses mnemonic instructions that can represent specific operations that can be then translated into machine code, which consists of binary instructions that the computer's control unit can execute directly. See, your DIY homemade computer is much like a schizophrenic dog. It tries to bring you a bunch of random things because it probably doesn't understand what you told it to do. Therefore, most machines have a central processing unit, or the CPU. The CPU is the brain of the computer, as it contains a control unit and a arithmetic logic unit, or an ALU, and now much like a non-schizophrenic dog, the control unit fetches machine code instructions from memory, decodes them, and coordinates the executions of these instructions in a reasonable manner. The ALU then performs the calculations and logical operations based on these instructions. Code and data reside in various types of memory, of which the primary form is random access memory, otherwise known as the spec on my computer most people for some reason always ask me about. This type of memory holds the currently executing code and data. The code and data that are not currently in use are usually stored on secondary storage devices like hard drives or solid-state drives. At the lowest level, the computer's hardware consists of electronic circuits built using components like transistors. Transistors process binary signals by using p-channels and n-channel MOSFETs in a CMOS inverter configuration. The PMOS and NMOS transistors have three terminals: source, drain, and gate. When the input signal is logic 1, the NMOS transistor conducts, connecting the output to ground, which is logic 0. When the input signal is logic 0, the PMOS transistor conducts, connecting the output to power supply, which is logic 1. This complementary behavior allows for the precise control and manipulation of binary signals in digital circuits, enabling the construction of complex logic gates and computational components. To us, transistors act as switches that can be turned on and off, representing the binary values 1 and 0, and in a larger scale sending information in the form of bytes. But how will a machine know if a given byte is an instruction or not? The number may represent an arithmetic operation, or it may represent how many times I revisited a specific website. Well, the bytes always show up in a very specific order in memory, and using things called memory addresses, the computer knows when the instruction byte begins, ends, and what exactly comes after it. Modern processors usually have much more convoluted and expansive instruction sets, so naturally the addresses and instruction bytes will also be processed on a larger scale. The computer interprets these on-off states of transistors as meaningful signals using a digital logic system. I kind of wish I had these logic systems so I can interpret the signals from things called logic gates are fundamental components that process binary signals in a computer. The most common types of logic gates are AND, OR, and NOT gates. Looking into each one, an AND gate takes two binary inputs and produces an output that is only true when both inputs are true. Transistors within the AND gate are connected in a way that allows current flow through the output transistor only when both input transistors are turned on. An OR gate also takes two binary inputs and produces an output that is true when at least one of the inputs is true, with the transistors within connected in a corresponding fashion. A NOT gate takes a singular binary input and produces the opposite value as the output. It is also known as an inverter. A transistor in the NOT gate allows current flow through the output transistor only when the input transistor is turned off. By combining these basic logic systems, more complex operations computations can be achieved. The binary data represented by the on-off states of transistors can be processed through these logic systems to do things like arithmetic, store data in memory, and execute instructions within a computer. Now keep in mind, my summary of this rather complex topic is very broad, meaning the The specifics of each instance may vary from person to person and from machine to machine. Regardless, now with the general process out of the way, let's take a look at an example. Here in my code editor, I have prepared a program that creates a simple guided user interface with this image of a cow. So now going back to the first step. On my Windows laptop, I interacted with the computer using input devices in the form of a mouse and keyboard. I then wrote the Python code in the development environment VS Code, which has its own Python interpreter. The code I wrote, including the GUI code for the cow image, is ultimately translated with an interpreter like CPython, which first translates the Python code into an intermediate representation called bytecode. This bytecode is a lower level representation of the Python code that is closer to machine code but is still platform independent. The bytecode is not a specific low level language like assembly, rather it is a set of instructions specific to the Python language and its interpreter. These instructions are designed to be efficient for execution by the Python interpreter. Eventually, the lower level instructions generated by the Python interpreter are converted into machine code, which consists of binary instructions that the CPU can directly execute. The CPU of my Windows laptop then fetches the machine code instructions from memory, decodes them, and coordinates their execution. As my Python program includes the instruction to create a GUI with the picture of a cow, the CPU executes these instructions, and the GUI is created and displayed on my Windows laptop, showing the picture of the cow. And this process won't be altered much if I replace the image of the cow with something else or ran a completely different Python program. Now, you may be thinking, but what about executions that upload stuff to the cloud or runs programs on connected devices like a USB or Ethernet deploying code to another machine? Now, generally, the initial process would still remain the same from input devices to binary code, but just how the computer will handle the output will be different. This may involve your machine interacting with network protocols, establishing connections, and transmitting data to remote servers. Those topics may be covered in a later video, as the point of this one was to give my viewers a general idea of how a computer physically reads code. And now once again, for real this time, congratulations! You have now been alleviated of your sadness. And if you still haven't, I prepared a multitude of sources in the description for your enlightenment.